Şu an gözüktü sanki.
Meryem masuk.
Okay.
Okay.
Hello, everyone again. Let me give you a brief introduction. I am Assistant Professor Şahin Coşkun from Eskişehir Osman Gazi University. Welcome all for morning session. Our first keynote speaker is Professor Dr. Mustafa Ürgen. He is from Istanbul Technical University, Department of Metallurgical and Materials Engineering. Here, he will talk about potential of cathodic arc plasma for surface modification and alloying. Professor Ürgen.
Yes, thank you. Thank you, Chairman. So I'll start once more from the beginning. This kind of things happen during this kind of online meetings. So we have to be prepared for such kind of problems that may arise. So it's not a big deal. So I'll start from scratch once more. So my talk, as the chairman has already mentioned, I am from Istanbul Technical University and working in the Department of Metallurgical and Materials Engineering of my university. And I have been involved in surface technologies and corrosion mainly. And I've been working in this field for more than 20 years. So the subject of this talk that has already been presented is the result of about 20 years of work that's been conducted in our group. So before going further, I would like to acknowledge the contributors to this work. There are two academicians. One of them is Professor Kazmanlı. He is at the moment the department chair of our department, and his contribution to this work is very valuable. The second one is Dr. Vladimir Straniski. He is from a very, very well-known institute in Ukraine, KIPTIS. And this institute is very well known for the invention of cathodic arc PVD technology. So we have collaborated with him within the scope of a TÜBİTAK project for several years, and he contributed very deeply into the study. I have started to work on this topic with my first PhD student, Erdem. He is now working in Böhlerit. Then we continue to work with Beril Çorlu, who is working now in ArcelorMittal R&D Center in Belgium. Then we continue to work with Erdem Arpat. He is working at the moment in Şişecam R&D section. Fatma also was one of my students who contributed to work. She is now an assistant professor in Bilgi University. Semih Öncel is one of the major contributors to this work, especially during his PhD work. He did really bring an advancement in the methods that we have been applying for the surface alloying. Sinan is also a contributor to this work. He did master's work with me. And Arkan is my last student who is still working on this topic. And I also want to thank the institutions that supported these studies. First, I have to start with NATO. We have established our laboratories with a project that has been through NATO Science for Stability. And then state running organization support, we further improved our laboratory facilities. And finally, we have been conducting several works with the TÜBİTAK supported projects. So now my talk will be outline of my talk. I'll start to talk about what is cathodic arc, because not so many people are very familiar with this technique. And then I'll talk how we can modify the structures of these coatings by using different methodologies during the deposition. And then I'll start to talk of our main topic, the potential of surface alloying by using a cathodic arc plasma. And I'll give some examples that have been conducted in our group for this purpose. So when we look at the cathodic arc plasma technology, it is being invented in 1966 during the development of a vacuum arc sorption pump. So what they were trying to do in this institute that Professor Dr. Streniski is, they were trying to develop a sorption pump. As you know, titanium is very active towards all the gases. So when they are conducting such kind of a work, they managed to burn a continuous arc on a titanium target. So, and then they patented this technology as an arc sorption pump. And then Anatoly Romanov and Andreev thought that this is a very nice technology for coating deposition, and they started to adapt this technology for deposition. So what they were doing is they were burning a cathode and they were creating a titanium plasma, and then introducing nitrogen into the environment. They managed to produce very well-known titanium nitride coatings. And then this technology is patented, and it was kept secret till 1979. On 1971, the Western world became aware of this technology by the transfer of this technology to a well-known American company, Multi-Arc. And then today, when we look at the potential of this technology, today this technology is the major PVD method for production of hard coatings. All the major industrial companies, Hauser, Balzers, Eifeler, whatever, they all have cathodic arc deposition systems that are mainly serving for hard coating industry. And in Turkey also, all of the companies that are doing hard coatings are using this technology. We got involved in this technology in 1993 through a NATO project that has been realized that has been supported by NATO. So from there on, we have been working on this technology from these different aspects. So let's switch to what a cathodic arc is. So as you see on the left, this is a cathode surface that when this arc is burning on it. So you see this blue lightning light movement is the movement of the arc on the surface. So while this arc is moving on the surface, it melts and evaporates the material, and it is converted in a very strong plasma. And since this is being produced in vacuum, we can control the environment for production of different compounds by introducing several reactive gases into the environment, such as nitrogen, methane, etc. So this is a schematics of a cathodic arc setup. So these are cathodic arc sources, as you see, these pink and red parts. And we burn these cathodes by using a very simple power supply that we use in arc welding. So this is a high current, low voltage power supply. So when we short circuit these two leads on the surface of the cathode, arc starts to initiate and starts to burn. So in this manner, we introduce into the environment the metal vapor that we want to work with. In the meantime, we can apply a negative potential to the substrates. This is a very important area for this research. I'm going to talk a lot about this. This we name as bias voltage. So the help of the bias voltage, the contribution of this bias voltage to coating structure and the properties I will mention deeply in the coming sections. So when the cathode burns, as you see, this is the low, very high speed camera view of a cathodic arc moving on the surface. So each cathode spot stays on one point in microseconds and then starts to travel all over the cathode surface, leading to melting and evaporation. In the meantime, we also have, because of the electrical field that is created here, lots of electrons, and these electrons get in contact with the metal vapor and it's convert them into ionized state. So we have a very highly ionized plasma that's almost 90–95% contains ionic form. In the meantime, there's also another issue that takes place. These are the droplet formation. When this metal melts, there are small metal pools that form on the cathode surface. They may spit out nanoparticles in micron size onto the substrate surface. So this is one of the drawbacks of cathodic arc technology, this droplet formation, but it doesn't create a big deal mainly for hard coating applications. So, as I told before, you can apply a negative potential to the substrate surfaces. So what does this do? It helps us to further increase the energy of the ions that are coming to the surface. So normally when we don't apply any bias voltage, the energy of the ions that are coming to the surface ranges in between 19 eV to 160 eV. However, when we apply a bias voltage, then we multiply the voltage that we apply with additional contribution, and we can increase the kinetic energy of the ions that come to the surface up to 400 to 500 eV. So that's a very high energy. So by playing with the magnitude of this energy, by changing the voltage that we apply to the substrate, we can achieve different effects. So if we apply a voltage, a high voltage around 1000 volts, then the energy of the ions becomes so high that they sputter clean the surface instead of making deposition. And on the other hand, we can heat our substrate material by the transfer of momentum to the structure. When we decrease the voltage, then we can start with the deposition process. And when playing with the magnitude of this voltage, low voltage, we can also tune the structure of our coating. And even if we go voltages over 1000 volts, we can start to make implantation. And these processes are named as plasma ion implantation and plasma ion implantation and deposition. So as you see, bias voltage creates a very crucial role in during cathodic arc plasma treatments and deposition. So what happens when the ion and substrates interact? Lots of things happen. Sputtering happens, recoil mixing happens, implantation happens, and all of these processes result in local heating of the substrate material, which in turn may lead to local melting. And overall, we start from an atomic scale heating to bulk heating. So when I apply a voltage to the surface of my substrate, then I can have an additional effect that can be created by the application of this bias. This is heating. So how do we benefit from biasing during cathodic arc deposition? Generally, when you start to do cathodic arc deposition, you start with an application of high voltage bias. This high voltage bias results in etching and heating of our substrate material. So in this case, we get a very clean surface, we get some supplantation, and this is one of the main reasons why we have a very good adherence of the cathodic arc deposited coatings. So we ion etch the surface by application of a high voltage. Then when we reach the required deposition temperature, we lower the voltage and start the deposition. And by controlling the magnitude of this voltage, we can tune the density of our coating, we can control stress, we can control preference orientation, we can even end up with grain size refining. So this is a Messier diagram that shows us how the structure of the coatings varies with the energy. So the normal way of increasing the density and integrity of the coatings is the increasing of the substrate temperature. But we are limited to this increase to temperature because of the nature of the materials that we use. This is the melting point of the substrate material. So if you go half of the melting point of substrate, you get very dense structures. But on the other hand, we can change the story by the application of an additional energy that we apply through biasing. So when we apply biasing, we can have dense structures at low temperatures. So this is one of the biggest benefits of biasing in PVD metals. So when summary, you can attain a highly ionized metallic plasma, amount of which can be tuned with the arc current. We have a substrate biasing. We can tune it between 0 to 1,200 volts in conventional systems. So in this manner, we can have sample temperature depending on bias voltage, heat capacity, mass of the bombarding ions, thickness to volume ratio of the substrate, etc. So our main aim was, can we benefit from bias-dependent effects by modifying the coating structure and surface alloy? Here you see an example. So this is the tungsten carbide cobalt insert that is being subjected to cathodic arc chromium plasma by application of 1000 volt. As you see, you can increase its temperature in about 5 minutes to about 1,100 degrees. So this is a very powerful tool for heating the substrates. So we started to try to benefit from this effect. The first study that we have conducted on is that when you try to deposit these coatings on ceramic materials, the adherence of the ceramics to the metals is not very good. So you have to heat the substrate to very high temperatures. And also you have to make the surfaces rough, etc. And the additional thing is that we looked for very dense coatings that we want to produce on this non-conductive substrates. The idea was to deposit titanium metal on alumina substrates so that these titanium films will be further processed for sensor applications by using a porous non-ionic oxidation. So here you see the structure of the coatings that we have produced by using only a bias voltage of 100 volts, and this is 200 volts. So here you see the typical columnar structures of the titanium, the PVD coated materials. So this structure was not very valuable for us. So we wanted to convert it into a denser structure by recrystallization. So what we did is we applied a 1000-volt bias after this application to heat the substrate to 900 degrees. Because these coatings are very thin, 4 minutes of application of this bias voltage that led to the increase of the substrate surface to 900 degrees, lead to densification of the coating. And this helped us a lot in further utilization of the structures for sensor applications. So as I said, bias voltage has a dominant role on the properties of the coatings. So when you continuously apply a high voltage bias, as I said before, you end up with a very dramatic increase in substrate temperatures. So the idea was here, why don't we apply a pulse bias? What I mean is that we apply a bias for a microsecond period, and then we make an off period. So in this manner, we can pass the bias voltage, and we can benefit the positive role of high voltage bias without too much increasing the substrate temperature. And this methodology has been used very extensively in KIPT for the position of carbon-based coatings. So we switched to this system into titanium nitride coatings and try to understand the modifications that can be induced on the coating structure by using this methodology. So what we did is, in this case, we compared the coatings that has been produced by DC bias. This is the DC bias. And then 1 kilovolt, that means 1000 volt pulse bias. And then we also introduced argon into the structure. And what we saw is that when we have argon in the structure, and when we also apply pulse bias, we end up changing the orientation of the titanium nitride films that grow into 2-to-O direction. So these films are normally one direction oriented, but when we apply a high voltage pulse bias, we start to grow films in 2-to-O orientation, and additionally, we also got finer columnar structure. And then when we conduct a tribological test, we end up in a very interesting results. So here you see the coatings that are 1-1-1 oriented. You see a dramatic increase in coefficient of friction and high wear. But when these films are 1-2-2 oriented, the friction coefficients decrease dramatically and stayed constant for a long period of time. And also the wear that has been induced on the substrates, on the coatings, dramatically decreased. So this was an interesting result, and we tried to understand the reason for that. So what we did is then a post-characterization of the samples that has been tested tribologically. And then we look at the wear debris. As you all know, the people who's involved in tribology knows that the character of the wear debris plays a very dominant role in the wear behavior of materials. So what we see is that the 1-1-1 oriented layers exhibited a nanocrystalline amorphous structure that has been very clearly observed from Raman spectra. So the coatings that has been produced under pulse bias, on the other hand, shows a nanocrystalline structure that is composed of a mixture of anatase and rutile. So this seems to be the main reason for this observation. So why? What happens when the surface is 1-1 oriented or 2-2 oriented? How does the debris character may change? So from the literature also we can follow that the debris in an amorphous structure leads to higher coefficient of frictions. On the other hand, when the debris are nanocrystalline, we get a very highly better properties with respect to tribological properties. So we end up with the conclusion that nanocrystalline debris give better performance with respect to their tribological behavior. So why is the question to be answered? So that means when you reach a nanocrystalline nature, the volume of the oxide that is produced on the surface should be enough for the conversion of these structures into a crystalline phase. So, and since these are defective, we can end up with the formation of lubricious magnetophases that show easier shear. When we look at the literature with respect to oxidation behavior of these materials, we found an interesting study which mentioned that the 1-1-1 oriented planes are more oxidation resistant than 2-2 oriented planes. So this gave us enlightened us in a way. Okay, then we end up with this as explanation. So when you run the test on a 1-1-1 oriented sample, the temperature that is created during rubbing doesn't allow the formation of a thick surface film because the oxidation resistance of 1-1-1 oriented grains are lower. On the other hand, when you conduct the same test by using a 2-2 oriented films, these films are oxidized with a higher rate that leads to the formation of nanocrystalline structure because of the higher volume of oxide materials that is formed on them. So that was the idea, and this was it's a very good study that shows the role of orientation on tribological behavior and especially also on the oxidation behavior. Then we switched to another area. Okay, so like we said, we can also use this increased temperature behavior that can be obtained by the application of high voltage bias for surface alloy. So what we said, we can heat our substrate to any temperature that we require. We can coat any material that is available as a cathode onto the surface of our material. So why don't we coat and heat the material so to induce a diffusion between the substrate and the coating material? So we started with an industrial problem. This is a very well-known problem in tungsten carbide cobalt hard metals. These materials, as you know, the cobalt is the binder phase for the tungsten carbide cobalt structures. So when you use these in certain applications, in corrosive certain applications, the cobalt leaches away, leaving away behind the tungsten carbide skeleton. So this really creates problems for their usage in such corrosion environments. So what do people do for overcoming this problem? They change the composition of the binder. They alloy the binder with nickel and chromium for increasing their corrosion resistance. But cobalt is a very easy binder to be used in tungsten carbide cobalt system, and the technology is very, very well established. So we said, okay, let's have again cobalt binder tungsten carbide cobalt set sample, but let's try to alloy this cobalt binder phase by the method that we are proposing. That means we deposit chromium on it, increase the temperature of the substrate so that an alloying between cobalt and chromium takes place. So for that, we designed an experiment. In this case, when we apply 150 volt bias, we deposit. When we apply 1000 bias, we heat the sample. So we coat bombard in this manner. We made a chromium coating, bombarded for allowing the diffusion to take place. And for this purpose, we use a chromium cathode and cathodic arc chromium plasma. And these are the samples that we are using. We used a 10% cobalt containing sample. And here you see how effectively we can increase the temperature of our substrates by using in time ratios of seconds. We can increase up to 1,100 degrees. We can increase to 850 degrees. And we can tune this temperature by changing the bias voltage. And then by application, after application of this method, we characterize the surface of our coating materials, tungsten carbide, cobalt. This is the original surface. These dark areas is the cobalt phase, the light areas are tungsten carbide phases. So these are the scanning Auger analysis that are being taken from these spots. When we alloy the surface, we found out that finally these areas where cobalt is present has also chromium in their structure. So this seems to be that we manage to alloy the cobalt phase with chromium. Another interesting output that we didn't expect to see was the formation of eta phase during this process. Eta phase is this compound. This is a complex cobalt tungsten carbide phase that forms as a result of carbon deficiency in tungsten carbide cobalt system. And this is normally not a wanted phase in tungsten carbide cobalt structure because it embrittles the material. However, if this phase only forms on the surface, on the other hand, it is also beneficial for a lot of property improvements, such as hardness increase, better cutting performance, etc. So for testing, if we have achieved our aim, we have conducted corrosion tests. So this is the surface of the sample before the treatment and before the corrosion test. When you subject this material to corrosion test, you see for 24 hours at 50 degrees, you see that cobalt phase is being leached out, leaving behind tungsten carbide particles that fall into the solution and deteriorates the mechanical properties. And we look at the cross-section of the same sample, we see a dramatic effect of corrosion that expanded up to 50 microns of depth. You see all these dark spots, the areas where the cobalt is being leached out. So when we do the same test with the samples that has been treated, we didn't observe any kind of this process that's been taking place. So it showed us that we successfully managed to alloy the surface, alloy the cobalt phase in the tungsten carbide cobalt samples for improving their corrosion resistance. And we have a patent registered patent on this story. And then we continued to study on different alloy systems by using the same methodology. We tried to modify copper surfaces by alloying it with aluminum. We tried to modify aluminum surface with copper. Chromium silicide, we tried to form cobalt chrome study, as I have already mentioned. We tried to alloy niobium with titanium, that for superconductor materials. The method worked successfully, though. We can manage a very fast alloying, especially when we work in the solution region. So, however, a more controlled process with respect to temperature of treatment, and because you apply a very high voltage, bias voltage, during your modification, you somehow also sputter away some of the species that are formed on the surface. So we thought, can we further improve this method? And when you look in the literature, as I said, the cathodic arc plasma contains lots of electrons. Normally, these electrons, under operating conditions, go to the walls of the chamber, and it is grounded. So they are useless. They only heat all the walls of the substrate, all walls of the vacuum chamber. So there are a few studies in the literature that utilizes these electrons for heating of the substrates. So what they do, they cover the surface of the cathode, and then instead of applying a negative voltage to the substrate, they apply a positive voltage, so that the electrons that are created in the cathodic arc plasma specifically come to the surface of the substrate materials. That will lead to heating of the substrates. So this has been a method that has been used in some cathodic arc PVD systems, but mainly for heating the substrate with electrons instead of using ions. So we said, okay, we have an opportunity. We can direct the electrons or ions to the surface of our substrate material by changing the polarity of the bias voltage that we apply to the surface. So why don't we make it in a cyclic manner so that we can use both electrons and ions that are coming to our surface? So this is also a patented technology of our group that has been registered. So we started to use an AC bias voltage. So when you apply a AC bias voltage, in the positive cycles of the AC bias, electrons comes to the surface of the substrate. In the negative cycles, on the other hand, the ions in the plasma that come to the surface and they deposit. So this was the idea that we started to apply. And the first study that we have conducted for this purpose is aluminizing of Inconel. Inconel is a nickel alloy, as we all know. So these materials are used for high temperature applications, and the surface of these materials must be protected from high temperatures by a thermal barrier coating. So for a good adherence of thermal barrier coating to the substrates, we need a bond coat. These bond coats are metallic in nature. They can be metal, chromium, aluminum, yttrium-based structures that can be produced by plasma spraying or E-beam operation, or cathodic arc PVD. So another application is, in this case, is aluminizing the surface of the nickel alloy to form a diffusion-based layer mainly composed of nickel aluminides. And the thickness is required for this purpose is about 40 to 100 micrometers, and the preferred phase is nickel aluminum phase. So as I said, there are lots of processes for aluminizing these materials, pack processes, CVD processes. I'm not going to go into details. So we started to try to apply an alternative method for aluminizing of nickel alloys by this method that we have developed. We named this method as electron metal ion treatment because we are both utilizing the electrons and the metal ions that are present in the cathodic arc plasma by using a alternating current bias surface. So when you look at the behavior of diffusion between an aluminum and nickel, it shows an interesting behavior. When the aluminum content of the nickel aluminum alloy is lower than 50 atomic percent, nickel diffuses into aluminum, and this is named as a low activity process. So when nickel diffuses into the aluminum, you end up with this kind of a structure because nickel comes from the substrate material and goes into the aluminum layer. So in between, this layer starts to appear. This is the layer that has been the remnants of chromium compounds that are present in the nickel alloys. On the other hand, when the composition, atomic percent compositions goes behind 51%, if aluminum content becomes high, the process starts to become high activity And in this case, aluminum diffuses into nickel. So when you look at these aluminizing processes, you see that both processes should take place concurrently, because at the beginning of aluminizing, we have a high aluminum content, low aluminum content, then it switched to high aluminum content. So what we did, we applied a 28 volt AC voltage. By controlling this voltage, you can tune also the temperature of your substrate, and we end up with the formation of an aluminum-rich nickel aluminite layer. Here you see the thickness of total layer is about 23 microns. And because it starts with a low activity at the interface, and afterwards it starts to become high activity, and we see that chromium segregation starts to get dispersed by changing the mode of diffusion. When we further increase the temperature, we also show that we also end up with having an aluminum-rich nickel aluminite formation on the surface. And again, this process started with a low activity process. And then as you see, these particles are chromium particles that are segregated at the interface, start to get dispersed in the structure, and we can increase the coating deposition thickness to 42 microns. And then when we further increase the temperature, in this case, because of the high diffusion rate of nickel does not allow aluminum content increase above 50%, we always stay in the high activity region, and we also have, in this case, nickel-rich nickel aluminite formation. So this shows us that there is a potential of this method for production of aluminite layers on nickel. So then we tried to also apply this method to titanium. As you all know, titanium and its alloys are used in high temperature applications because of their specific strength at high temperatures. However, their erosion and poor oxidation behaviors about temperatures of 700 degree is a problem. So one of the main ways of overcoming this problem is to alloy their surfaces with aluminum, or you can change the alloy composition or produce beta alloys or highly alloyed systems. They are expensive, and also they bring along very high brittleness. So another way is to aluminize the coatings to produce an aluminite layer, especially for oxidation, improving the oxidation resistance. And here you see the literature survey that's being conducted for aluminizing of titanium, I'm sorry. And as you see, standard deposition methods end up with very low coating thicknesses. Laser surface alloying and then heat treatment ends up with very thick layers. Aluminizing plus heat treatment also ends up with thick aluminite layers. So we try to understand this process and apply aluminizing by this method and at different temperatures to observe the effect of this method on the production availability of aluminides of titanium. So we started with a low temperature, rather low temperature, 1100 degrees, and we analyzed our samples for 20 minutes under these conditions. And here we see a double layer structure. We are in the titanium aluminum 3 plus aluminum layer. That shows us that there is an aluminum deposition that has been taking place on the top of the coatings process that limits the diffusion process. And then we increase the temperature to 1200 degrees. Interestingly, the coating thickness didn't go beyond too much. It's limited to 15 microns. And in this case, we obtain titanium aluminum 3, titanium aluminum 2 compounds. And then when we increase the temperature further to 1300 degrees, we see a tremendous increase in the diffusion rate of aluminum into titanium, and we end up with having a surface layer that has a aluminum content around 30% for extending beyond 65 microns. So this is an interesting story and needed to be explained by the knowledge of physical metallurgy and diffusion. So when you look at the phase diagram of binary phase diagram of titanium aluminum system, and also to the diffusion behavior of aluminum into titanium, you see interesting things that are taking place. First is that in alpha titanium, the diffusion of aluminum in the solid solution region is very high, and then it becomes very low. In beta titanium, again, we have a very high diffusion rate in the solid solution region, and then it may change depending on the process. So let's start with the alpha region. So when you conduct your samples, this test at 800 degrees, you start to form alloy titanium with aluminum up to a content of 10% approximately. So if you stay in this range, you just have a titanium aluminum solid solution. So when you reach here, the solubility, the diffusion of aluminum into titanium dramatically decreases. And then you start to deposit aluminum onto, metallic aluminum onto the surface, and your diffusion couple switches to the other end, of the aluminum end. And as you see, there is very low solubility of aluminum, titanium in aluminum. So we start to form here this titanium aluminum 3 phases plus aluminum. That was what we were observing for the cases of 800 degrees and 1100 degrees. So in here, the interesting story is this region. In this region, there is an alpha beta region. This narrow gap is composed of alpha plus beta titanium. So when we go a temperature beyond the alpha beta transition, the diffusion process takes place very fast till we reach this region. That's what we have observed. So when we come to this region, around the beta particles, alpha phase starts to form that limits the diffusion again. So we again switch to the aluminum-rich region because of the position of the continuous deposition of aluminum on the surface of the material. So our diffusion couple changes from titanium, diffusion of aluminum into titanium to diffusion of, diffusion of titanium, aluminum to titanium. So this is a switching of diffusion couple by changing, by coming to a region where alpha aluminum is present. So when you conduct your tests under this region, when you cool down your samples, you end up with the formation of these phases. But when you try to go further, you end up coming to here. So when we look at the 1300 degree C, very high diffusion rate, we see that there is no limitation that is being aroused by alpha aluminum. So we extend our diffusion zone to very high regions before coming to this aluminum-rich surface layer region. So with this, I want to end up my talk. Cathodic arc plasma is a very powerful tool, both for deposition and also for surface alloying. We can benefit both from the ionized state of the ions in the coating on the plasma and also from electrons for converting our surfaces, coating structures, for modifying our structures into highly variable surface alloys or coating processes. So these processes mainly rely on physical metallurgy principles. By using our proper tuning of our process, by using these principles, we can obtain different binary alloys, ternary alloys that are difficult to produce by conventional method. Another advantage of this method is that it's being conducted in vacuum, so that we don't have any oxidation and contamination problems. With that, I want to end up my talk, and I want to thank you all for your attention. If you have any questions, I'll be glad to answer.
I would like to thank Professor Urgen for his great talk. Yeah, actually, I had a small question, but yeah, you mentioned about in your conclusion. So, what we can say about the conventional techniques on how can I say, how to difficult to make binary or ternary alloys on coating with the conventional techniques, Professor?
Yeah, okay, for alloys that we are very familiar with copper, aluminum, etc., you can easily make them by casting and other methods. But if you want to make it surface alloying, you can also make it very simply by immersing these alloys into molten aluminum bonds. But in these cases, the problems starts to arise because of environmental issues. So when you conduct this, when you heat aluminum to above 650 degrees, it starts to melt. But when you want to increase further this material in the atmospheric environment, you start to oxidize the material dramatically. So it doesn't allow you to go beyond certain temperatures. The other thing, exotic materials or high temperature, melting temperature materials like titanium, niobium, or zirconium, it is very difficult to work with these materials without using a controlled atmosphere. So this method that we are being using is both valuable from two perspectives. One, you can conduct very nice experimental diffusion studies in a very controlled manner by using these methodologies. And also you can produce metastable structures with these methodologies. And it's a kind of a tool, both very valuable tool for research, but also for technological applications.
Thank you, Professor. And the chairman of our conference, Professor Atesh, yeah, he will give a small thank for you.
Hello, everyone. I would like to thank Professor Mustafa Urgen Hocam, who is the most important academics on this field. We try to follow him. We are very happy to listen him again, and we say best regard and wishes. Thank you very much, Professor.
Thank you for your nice feelings. I also feel the same way towards your group and for the conference. Thank you very much.
Thank you.
Dear audience, there will be a small change in our schedule. The next meeting will be given by the Professor Dr. Hüsnü Emrah Ünalan. It's actually an honor for me to introduce him. He is my master's and PhD degrees advisor. He is from Department of Metallurgical and Materials Engineering of Middle East Technical University, and he will give us a talk on metal nanowire networks, promises, facts, and challenges. Professor Ünalan. You can share your screen and we can continue.
Okay, I believe my screen is visible. I would like to start by saying good morning to everyone. This is Hüsnü Emre Önalan from Middle East Technical University, and I will be talking about a material and a material-related technology in this morning. So let me switch to the laser. Okay. So I've been in METRI for the last 12, 13 years, and I'm leading a group called Nanomaterials and Devices Laboratory. And our intention here is to make transparent, unconventional, first of all, transparent, flexible, textile and paper integrated devices. And we are trying to investigate and develop, if possible, wet processes so that we can make these things over very large areas and in a very cost efficient way. And some part of the work, actually the biggest part of the work involves one-dimensional materials, and you can call them as nanowires or nanotubes, and here are some of them. Today's talk will be on silver nanowires and copper nanowires on the conducting end, and carbon nanotubes are also there if you are dealing with multiple ones. And in, like as a complementary device material, you can also make use of semi-conducting nanowires, and in that regard, we also investigated zinc oxide, germanium, and silicon nanowires. And underneath each title, as you see, we are not just dealing with the syntheses, but trying to, as I said earlier on, incorporate these materials into the devices, and the examples are given below. And I will be talking about transparent conducting electrodes, which we develop silver nanowires, the silver nanowire networks for. And these transparent conducting electrodes are everywhere, commercialized, used extensively. And this is in your TV, that might be in the solar cell, in the non-silicon based ones. That is in your cell phone screen, that is in your cell phone touch part, and everywhere. So it's an important material. It's a big industry, a big market on the side as well. And the well-known and the most commercial transparent conducting electrode material is a ceramic material, as you see over here, indium tin oxide. And there are some derivatives, if you wish: the aluminum doped zinc oxide, gallium doped zinc oxide, fluorine tin oxide. These are the derivatives, but basically ceramic in nature. And obviously, due to the drawbacks, which I will like to keep that for the next slide, due to the drawbacks, people are developing, including ourselves, different materials. And some examples are listed in here: graphene, carbon nanotubes, polymers, metal meshes. And one of the other alternatives are the metal nanowire networks, which I will be speaking mainly about today. So with these sticks, so-called conducting sticks, we are going to make a film, or a film-like material, and we are going to have conductivity. So some of them are going to touch, which is going to be regarded as percolation, and some remainder parts are going to be empty. So the light is going to transmit, and eventually we're going to have a film which is both conducting, lateral, and that is going to be also optically transparent. Right, so that is number one motivation. The number two motivation is the electronics are getting more versatile. So they are not just silicon based, they are now flexible, sometimes body integrated, sometimes textile integrated. So typical silicon based electronics are going to be cannot be used for that purpose. So we need different materials. We need some stretchable, flexible materials. And in this SEM image, on the bottom right, as you see, ITO cannot survive if you do a bending test. And if you also at the same time measure the resistance, as you see over here, the resistance gets lost, or I should say, like diverges, or orders and orders of magnitude after a few banding cycles. But in contrast, as you see over here with the blue and the black, there are some alternative materials. One of them is the carbon nanotubes. Graphene would be the same, I believe, and also the blue one in here is going to be the silver nanowire thin film, which I will be talking about. So as you see, different material, and strain is no concern. Its flexibility is no concern, and it survives many number of cycles without breaking. And we all know, I believe, that indium is getting scarce. One might say that silver is right next by. It is true, but 100 milligrams of silver nanowires can coat a meter square of area. So it is, in that regard, very cheap compared to indium. But if you followed up the recent metal prices, for sure gold increased a lot in the last couple of months, I should say. Silver is also increasing crazily, but even still, copper is, like very roughly 2 orders of magnitude cheaper than silver in bulk form. And in nano form, we use the salts of silver and copper, nitrides basically. So the salts are going to be cheaper if you would like to grow copper nanowires instead of silver nanowires. So silver nanowires are cheap compared to ITO in terms of processing and the films and everything. But copper is also providing another cost alternative material to silver nanowires. But in this slide, you can see the pros and cons of each type. So graphene thin films can be used. For sure, monoblock films can be made by CVD processes. So think of your screen. Your screen is like 20 plus inches wide, maybe even larger in your TV. So monoblock graphene films might be a problem, and then you might deal with the patchwork concept. But in that case, the grain boundaries become a problem. As another alternative, single wall carbon nanotube thin films arise. Just metallic synthesis is not yet, as far as I know, established. So there's going to be always semiconducting nanotubes in the game, and that is going to give you the junction resistance. So in our case, there are both silver and copper nanowires. Roughness is a problem for both. Chemical instability is a problem, especially for both, for sure, but especially for the copper. That's why I write with red. Oxidation problem comes into play. Silver is neutral, copper is colored, so it's giving this. You will see in my forthcoming slides, it's in red in color. So if it is a concern for light emission, for instance, that needs to be taken care of. And stability. This is environmental stability. I will talk about that as well. So these are the problems that are associated with the metal nanowires. In contrast, on the ITO, cost that is both due to the scarcity of indium and the processing. So high performance ITO is still sputter deposited. Chemical instability. It's an oxide material, so you might need to take care of the chemical instability. Mechanical constraints. I talked about that. And since we say that it is sputter deposited, for sure roll-to-roll sputtering processes are out there, but it's not a cheap process to roll-to-roll deposit this thin film, so size limitations arise if you deal with the ITO. So let me switch the gears and start talking about how we make these materials. So we make use of simple solution-based processes, so for silver and copper, so I will further discuss the copper later on. And for silver, as you see, we just mix chemicals, we do some temperature adjustments, and growth is a bit different than conventional FCC structured silver. So in here, rather than having a cube, we're having a pentagon. So we start with multi-twin particles, and a polymer dictates or controls the growth direction, so that the newly added silver allows you to grow in 1D to get a nanowire eventually. And when we started with Dr. Coşkun in 2009, I believe we were getting 40 milligrams of nanowires. But with the forthcoming processes, projects, necessities, we now enlarged our growth, so we can get more than 2 grams of silver nanowires easily in 2 hours. So scale up was possible. If there is demand, certainly we can also increase this the growth further on, or at least multiply the number of synthesis setups very easily. After the synthesis, solution-based methods are used for their purification because we have some polymers to get rid of. And we also have some particles, since the synthesis doesn't give 100% nanowire growth, but you have some particles on the side, so you need to remove them. If it is small-scale synthesis, centrifuge might work, but if it is gram or liter scale in solution, that might need to be taken care of using some other methods rather than centrifugation. And then we spray coat these things onto the substrates. We can control the density of nanowires. Density of nanowires allows us to control the transmittance and at the same time the conductivity, or if you wish, the sheet resistance of these materials. And I should also show this. These materials are infrared transparent, as you see over here, whereas the conventional typical ceramic ITO is not. And after the deposition, there has to be some treatments. Why? Because even still we remove the polymer, we might have some polymers around the nanowires. Plus, you need to improve the nanowire junctions. So here, as you see, with our French collaborators, so this is in situ resistance measurement. As you heat up the thin films, as you see, no matter what the starting resistance is, if you reach the temperature of around 250 degrees C on a heated stage, your resistance decreases orders and orders of magnitude. And in reality, if you do this in a furnace, so we are doing batch processing, so we cannot really heat everything on this stage. So this is slide, the image C is 200 degrees annealing, and image D is 300 degrees annealing. So we, rather than trying 250 degrees, in practice, we are annealing the nanowire thin films at around 200 degrees Celsius. So as you see, with the annealing, you gain the sheet resistance, and at the same time, transparency is not changing. And as you see, you fuse the nanowires to each other, and eventually you get a typical of almost 90% transmittance in 550 nanometers wavelength, and that gives you a sheet resistance of 10 ohms per square reproducibly. That is quite highly competitive to the ITO. And during the measurements in France, what we have also discovered is that if you heat it up and if you cool it, you can get the temperature coefficient of resistance. So the bulk silver has 3.8 10 to minus 3 per Kelvin. And the nanowires, for sure, it changes with the network density, but it gives you, at least in the order of magnitude, similar temperature coefficient of resistance value. So this is also telling us that as metals, like as the resistance increases with temperature, on the side, you can use this material as a like temperature sensor. So you can make flexible, stretchable, and transparent temperature sensor with this material. Okay, so let me move on with some of the applications. So one of the applications that Dr. Coşkun made in the early times was making an organic light emitting diode. So a typical diode, so this is one layer diode, is fabricated in conventional case on ITO. The whole transport layer PEDOT-PSS comes in, and an emission layer comes in, and top contact comes in, and it's a bottom emission device. So we need to replace this ITO. But when you look into these films of nanowires, you would immediately realize that there is a roughness issue. Right, so this needs to be prevented first of all. So you're gonna put 100 nanometer thick polymer layers, and the roughness is, as you see, there are 3 to 4 to 5 nanowires on top of each other in some certain locations. So 100 nanometers of polymers will certainly short in these points, and the electric field distribution will not be uniform. So this roughness issue has to be prevented. So when we look into the literature, people tried putting polymers, putting nanoparticles to minimize this roughness, or doing like a potato stamping, doing the stamping process to get rid of this roughness. And as you see, some other applications in here, putting ITO particles, putting zinc oxide particles to polarize the ITO surface. So we said that, okay, putting ceramic particles, putting an extra material is okay, it works. But I mean, since we have P.PSS for the whole transport layer, why don't we engineer the P.PSS layer thickness, and then we can use it as a monoblock whole transport layer and the charge transport layer as well. So what Dr. Coşkun did was to change the P.PSS concentration and play around with the spin coating parameters, as you see, to planarize the film that we deposit on top of the silver nanowires. And voila, the result is, as you see, this is a control sample made with the ITO, and this is the control sample made with the silver nanowire networks. And this was, let me assure you, this was one of the first OLED papers dealing with silver nanowires back in 2013. And P.PSS is a problem. So in 2014, Sigma Aldrich introduced a non-acidic version of the P.PSS. But if you use a typical conventional 4083 or pH 500, these are acidic P.PSSs. And as you see, if you keep them for long enough on top of the nanowires starts getting etched. If you don't put the polymer, if you leave the nanowires over the bench, leave them, as you see, like you start getting some dimples on top of the nanowire. So certainly there is a stability issue. And in fact, this stability issue is not just for nanowires, not just for nano-sized materials, but also for bulk materials. And this is called as tarnishing and known for years. In that case, it's a competition between sulfurization and oxidation, so-called tarnishing. For sure, this necessitates a lot of like tens of microns of material. And unfortunately, in the nanowire network, we don't have this much thick material. So we have to be very much, very, very careful on protecting the nanowires against this sulfurization and oxidation issue. And as you see, the sulfurization also is acting on nanowire networks. So it's again a competition between oxidation and the sulfurization, which eventually completely kills the network, and you cannot read any resistance or conductivity, if you wish, from these thin films. So that is the environmental stability. Let me talk about another instability. So this is electrochemical instability. So if you are going to make any electrode for instance, like energy storage or another optoelectronic device, for instance, like electrochromic displays, you need to apply this potential in a solution or in an electrolyte, if you wish. So if you do this on top of silver nanowires, as you see in the first cycle, as you see, there is an oxidation, which is irreversible. If you go to the second cycle, as you see, you cannot really read current because you completely oxidized the silver nanowires irreversibly, and your network is lost. So we need to also take care of this electrochemical instability issue in addition to the environmental instability issue. And in order to deal that, we started a project with our Korean colleagues to encapsulate nanowires with a noble metal, which I will be talking about in a second. So for that, let me just briefly introduce you our energy storage device, so-called supercapacitors. And these devices are complementing batteries. Batteries have high energy and supercapacitors have high power. So what does that mean? If you're making a car, for instance, like with the supercapacitors, they go fast. With the batteries, they go longer. And they are usually used in complementary to each other. And the idea by then is if you have a transparent material, you can play around with the parameters, right? So one of the parameters is that we would like to see the amount of the charge that is remaining in this energy storage device. And this Duracell was our clue where we got the idea is that you short the battery and with resistive heating, and you engineer or you monitor how much charges remain within the battery. So that the idea was like, if you can do this in a supercapacitor, if it changes color, if it is empty or if it is full. And the answer to that is yes, it can be done. And if you use polymers, the color options are very many. And when we looked into the literature, typical electrochromic materials are oxides and polymers. And oxides or polymers are also electrode materials in the supercapacitors in the subfield of so-called pseudocapacitance, right? They have very large capacitances, for sure, but some problems exist. Oxides are not that conducting, and the polymers are not that stable. So if you like engineer these, you can make alternative materials to typical carbon-based supercapacitors, which operates with double layer principle. So the nickel oxide films are out there for electrochromics. Vanadium oxide is an even novel one, which gives multichromic. So it gives you different colors. It's not just 2 colors, but 4. And tungsten oxide is the most known, the widely known typical one on the oxide family. And for the organics, and these are commercialized, polyaniline and the P.PSS are out there for sure. The color options, they have limited in color, so blues and transparents, and greens and transparent. So why not? We have some other colors, so why we cannot engineer this process? So with the colleagues in the chemistry department, they have these very different fancy polymers that are solution processable. So on top of the silver nanowires, we can like spray coat these polymers. And these polymers are, as you see in the ground state, in the reduced state, or if you wish, it is very bright green, as you see over here. And then when you heat it, when you, charge it or you oxidize it to 0.5 volts, why 0.5? Because we had to stop there for unprotected silver nanowires, as I told you earlier on. When you put it to the oxidized state, it is becoming completely transparent. So this color change can also indicate the state of the charge. So these are typical cyclic voltagrams. Don't want to get into too much details, but as square or as rectangle is, as better the capacitor, or as small as is like a resistor, and it doesn't really have a storage capability. So as you see, once we put the polymer, it gets more and more rectangle-like. For sure, there are some storage for the silver. I believe it's due to the oxidation. There are 2 oxides of silver, as you know. One is reversible, but the other one is reversible. So that is the Ag2O. So it can oxidize, but the current is very limited. So the storage very limited as well. So, but our polymer completely drastically changes the storage capacity. And on the bottom, you have these charge-discharge curves. And this thing is as triangle as this means that you can charge and discharge in a symmetric fashion. That means that your device is reproducible. And with our polymer, we don't really have so much deviation from the triangle behavior. So that was quite a promising fact. And these things are on plastic substrates, right? So these things are very flexible. And the storage characteristics, as you see, doesn't really change with the number of bending cycles. And the capacitance is low. That is one of the problems associated with the polymers. Nothing can be done on that, but it gives you some other benefits like flexibility. And on the right-hand side, as you see, these materials can be cycled for, in this particular example, we cycled for 20,000 times and with no change in the specific capacitance. And I surely believe that we could even go longer. So they are very stable storage materials. And we wanted to expand this thing. So the next polymer, again, thanks to our colleagues in chemistry, now they developed this blue polymer as an alternative to the P.PSS. The characteristics are even better with these polymers. So they can charge and discharge and can do this very many times, and they can hold very large current densities. But again, the storage is low, so you're below 100 farads per gram, where in fact you can get more than thousands with the metal oxides, and with the carbon you can typically get around 200, 250 if you have very large surface area carbon. So you can put into this order of magnitude, not even order, but you can put this in line with other materials. So polymers are on the weak side, but it gives you, as you see, some other benefits. And this polymer was also highly stable, so we charged this thing for 12,000 times, but that was very highly stable. So, but 0.5 volts was our limit. So we would like to push this voltage to 1 volt or excess if possible. But we certainly cannot make this on silver surface. But then the idea was putting a noble material. Platinum and gold came into play in that regard. That's what we developed with our Korean colleagues. So in this slide, you see our platinum coating. So we engineer, again in solution, few nanometer thick platinum deposition on top of silver nanowires. And as you see, these plots are, forgot to write in here, but this is 85% relative humidity. This is 75 and this is 43. As you see in all cases, like the bare silver fails, but in striking contrast, the platinum deposited networks are very highly stable. Temperature-wise, the situation is the same. Room temperature, like the bare one dies in 3 months almost. I mean, exaggerated temperatures, as you see, even 150 degrees C in like 10 hours start degradation. But if you have platinum-coated nanowires, degradation is not prominent at all. And the microscopical images are telling us the same. Our networks in the platinum shell layer, so these are core shell, core silver, shell platinum case, they are highly stable. And one of the other measures that you can quickly see if they are stable is just like the drop a solution of hydrogen peroxide, and as you see, failure automatically happens on the bare, whereas the one with the platinum survives. And as you see, the nanowires completely disappears and gives you these dots, whereas with the platinum coating layer, network structure stays almost intact. And the next thing was to push this thing. So 0.5 volts was our limit. So can we push this to higher potential? So 1 volt or 1.5 volts. These devices do survive. So we try different materials. So this is polyaniline. So as you see these drops, and I believe there is some sheet-like coating also onto silver platinum nanowire thin films. So it is increasing the stability window. So the electrochemical stability is also increasing with the platinum deposition. Not going to spend so much time, but the scenario with the gold is the same. Again, with the solution methods, you can coat very thin layers of gold on top of silver nanowires to improve the electrochemical stability. I know platinum and silver is expensive, but trust me, we are putting a very thin 5 to 10 nanometers of gold and platinum, which is not increasing the cost so drastically. So let me move on with another device. So this time with the transparent heaters, with the Joule heating principle, if you like it similar to making a light bulb, if you apply a potential, a voltage to these thin films, they start heating up. And we investigated this by 3 different densities. And these are the heating characteristics. So for instance, with the highest nanowire loading, in 4 volts, which also allows 0.74 amps to pass, you get reach to temperatures of excess of 200 degrees Celsius. So what is this? This is like 3 watts, and it's getting 200 degrees Celsius. In your home, the iron that you use, you typically make use of 2,500 watts, and it typically gives you the same temperature. So imagine 3 watts that I'm spending, and imagine the 2,000 excess watts that an iron is spending. And these materials are also very quickly heat up and cool down, which is also another advantage. And always there is a limit. There's a temperature limit. I mean, I cannot go to temperatures of 600, 700, or 1,000 degrees. But, and the reason for that is, as you see, the thinner diameter nanowires with diffusion gets damaged, also eventually leading to a distortion of the network. But I mean, I can engineer this temperature. So as you see, the previous slide was 200 degrees, but if you do a gradual increase in the potential, the current and the voltage, you can go to temperatures as high as 275 degrees Celsius, which is enough for an iron or some other applications. And these devices are highly reproducible. These are on-offs for 5 cycles, which it doesn't really give any change in characteristics. And even if you don't coat the surface, as you see, if you keep the device on bench top for 2 months in ambient conditions, so-called, the characteristics do change a bit. But as I said earlier, we have some protection methods that we can apply onto these heaters. And this is a continuous heating graph. So as you see, you can keep the temperature in excess of a day with no change in the heating characteristics. They are flexible as well. And the good news is that it can also be integrated into the textiles, and you can start heating the textiles in a much efficient way. And that eventually led us to some patent applications and a startup company, so-called Nanomotive, located in the Metro Technopark. And then let me switch gears now, talk about the copper nanowires, because as I said earlier on, copper is a very cheap alternative compared to silver nanowires. But the problems are bigger these days with copper. So the long-term stability is a problem, and the facile, controllable, and cost-effective and scalable synthesis of high-quality copper nanowires was an issue. And I believe we also solved that to some extent. So for the stability, if you look into literature, what have been done is to put nickel on top, or zinc on top, or tin on top, or coating it with graphene or graphene derivatives like reduced graphene oxide. They were the solutions in literature. And I will explain our solutions into that. And let me start first with the synthesis. This is again a solution-based synthesis. It takes place in an autoclave. You just mix up solutions and put into the autoclave. After engineering, you get the nanowires at the end. And purification needs to be there afterwards, as we did for the silver, and we spray coat this onto anything, as you see in glass slide, on any size to get transparent conducting films. But the color, the orange color, is there in contrast to the silver, which was neutral in color. And similarly, we can control the sheet resistance and optical transmittance of copper nanowires as we did for the silver nanowires. Okay, so our solutions for the stability are twofold. One of them is an organic solution, and the other one is an inorganic solution. So once we were doing a patent search in literature, we came up with benzotriazole, which was used for the corrosion protection of bulk copper. And the idea immediately came into play. Why don't we use this BTA on top of the nanowire networks? And we just like mix it with ethanol, and we spin coated on the ethanol. The transmittance, as you see over here, is not changing at all. It's just like a slight variation, and the like the sheet resistance is not drastically changing either at the same time after the BTA deposition. And we also made an extensive stability study. As you see, we reported stability of copper nanowires upon BTA deposition in excess of a year, which is not really changing any at all in resistance, whereas the unprotected copper nanowires, as you see, diverges immediately after a few days, and which is becoming totally useless. And we also did some very intensive spectroscopic characterization on with our colleagues from Bilkent University. We looked into the temperature stability of BTA. It looks it is stable up to 150 degrees Celsius. This temperature is important. Why? Because this is a very important one for the organic electronics processing, which usually they don't subject these devices into higher temperatures of this. So the BTA is also stable in this regime, so which is very promising for us. And spectroscopically, we also monitored that, for instance, if you don't put the BTA, the dimples comes along, the surface, the smooth surface gets distorted. But when you put the BTA, the surface, protects, is well protected, and so does the what is dictated by the resistance measures upon the BTA deposition. And we looked into, as we did for silver, we looked into the temperature stability, humidity stability, stability under P.PSS, and voltage bias stability. And in all these measures, it is very highly performing among the non-BTA deposited copper nanowires. And in order to put everything into context, we also demonstrated a capacitive touch sensor. And as you see, it's like for a multi-touch, as we use these days in our cell phones, something if you touch with a conductive object, that can be a finger or that can be an aluminum foil, it detects the location, and it can be bent because it is on flexible PET substrates and works perfectly. But if you don't have BTA device and the sensors or the pixels die immediately and the device becomes useless in 3-4 days. Okay. So that was our organic solution. Let me talk about our inorganic solution. In this case, we are using atomic layer deposition to put thin layers of oxides. In this case, we tried aluminum oxide and zinc oxide. As you see here, the core is the copper, and the sides are the zinc oxide. And it's a ceramic material for sure. It increases scattering because the radii increases, so the transmittance drops a little, but certainly it protects the nanowires. And we immediately use this idea in heaters. So in a bare unprotected copper nanowire thin film, you can go to a high temperature as high as 100 degrees Celsius. But if you put 50 nanometers of aluminum oxide, you can go to excess temperatures of 200 degrees Celsius without any damage. So it also improves the thermal degradation history of copper nanowire networks. And in the Korean project, we're also trying to improve the stability of copper nanowires by putting metals. Similarly, gold and platinum are investigated on copper nanowires as well, and the results are very highly promising again. on copper nanowires. I'm not going to go into too much details. So let me move on to a little bit more into the physics, to the demonstration of nanowires in solar cells. So one of the losses in solar cells is, so if we all know that we need to use silver paste on the front surface, it needs to be thick enough to give you low series resistance for the charge collection, but it has to be thin enough so that it shouldn't really block that much of the light, because the sun-seeing side of the solar cells are decorated with these finger electrodes. So there is a compromise between, right? So our idea was there to use silver nanowire network on the front surface rather than using the typical finger electrodes. So they have high transmittance. So we tested this on a 2 centimeters by 2 centimeters solar cell. And I should assure you that we don't have a passivation layer. So this is not a proper solar cell. So the efficiencies that I'm going to report is going to be low, but the concept is verified. So we don't have a passivation layer on this, and we don't have any protection layer on the cell either. So anti-reflection layer is not there either. So we tried 3 different densities. When we directly coat on it, our cells with silver nanowires were not working properly, but similar to silver fingers, you need to apply a heat treatment for the ohmic contact formation. And when we put these materials, we monitor this with the series resistance changes. So if you heat this up to 400 degrees C in a very short time, it's like a minute or so, your series resistance gets improved and the device characteristics get improved. And there is also some plasmon effects that we discussed in the manuscript. But certainly, as I said, this needs to be improved further with an anti-reflection layer and a passivation layer, which I believe we will get much improved device characteristics by using front surface silver nanowires instead of silver fingers. And not only silicon-based solar cells, we apply this idea to organic photovoltaics. And the benefits are, so on the right-hand side, as you see, you have a typical aluminum top electrode, or it can be gold, but it's just literally blocking the light. But if you have silver nanowires, the device becomes semi-transparent, so you can shine the light from both ways. And we are now expanding this concept into perovskite and silicon perovskite tandem solar cells. And the summary slide is that we have, I think we can control the synthesis of these fellows. Now we can get grams of quantities of these materials after optimizing the growth parameters. And we also optimize the purification protocols. So getting figure of merit optoelectronic performance compared to ITO. So I think it's a rival now. And there were some problems of stability of environmental, mechanical, chemical stability issues. And I think we have also solutions to solve them for both for silver and the copper. And with this, I would like to spend some time on this discussion slide, what we have done and what needs to be done from further. And so you literally have sticks of a conducting matter, and you disperse the sticks on a flat surface, right? So the nanowire junctions are determining the conductivity, because the nanowires themselves are perfect conductors. I don't have any, rather than surface, I don't have any defect to scatter electrons while they travel. But once you have the junctions, there comes the scattering, and there comes the source of resistance. So this resistance has 2 folds. One of them is that in the junction region, you have the PVP. So PVP is, for silver, is a dispersant and a directionality agent. So that needs to be taken care of. So with the purification, we try to get rid of as much as we can, but not to 100% extreme, right? Because we make use of PVP for dispersion before spin coating. So that is number 1. Number 2 is that the fusing, right? So I need to get rid of the PVP, plus I need to fuse the wires to each other. So this is still a very important issue that needs to be taken care of. The other issue, the second issue, is the aspect ratio. So the percolation states that the longer and the thinner they are, the less materials you need to put on to get the percolative network, right? So if the further, sorry about that, the further studies should be conducted on improving the length and the diameter of the nanowire. So they need to be thin, but in that regard, the strain effect starts dominating. And we see in the papers that nanowires thinner than 50 nanometers are not that stable in ambient conditions due to the strain effect. And so you have to, this is a sacrifice again, like they cannot be thinner than 50 nanometers, but if they are thicker, haze also comes along. So if you're going to make use of these materials for a transparent conductor, you have to make also, you have to pay attention to the haze factor. So thickness and the haze are competing with each other in this regard. And the other thing is that we spray coat these nanowires onto substrates. And as you see, you only create a conducting path, and most of them are not functional electrically, plus optically they are blocking the light. So you need to remove them by some means. So that is another problem that needs to be taken care of. And the last part, as with each new and novel material, most people that are working on the synthesis should direct themselves to make use of these materials. Like more devices should be demonstrated with large area devices, new concept devices, high performance devices, so that we understand the pros and cons of these materials better and better. So I think these are the 4 remarks that I should make on these materials. So in my last slide, let me thank to my collaborators over from physics department, chemistry department, EE department of METU, and chemistry department over Bilkent, and some abroad from France and from Korea. To my students as well. This is an old image, I know, but I wanted to show this image because I would like to commemorate our lost student, master student Ece, in this presentation. Rest in peace, Ece, and thank you all for your attention, and I will be happy to answer if you have any questions. Thank you.
Thank you, Professor Nalan, for this inspiring talk. So I guess the chairman of the conference, Professor Atesh, will say a few things. Yeah.
May I?
Yes, sure, Professor.
Hello, Dr. Ünalan. Thank you very much to attend this conference. I would like to thank you to you and your team, especially your support. Aside from your study, we learned lots of things. If you give me a permission, I would like to ask a question related to your presentation. What are the challenges for other metals to be synthesized as nanowires and used in optoelectronic application? I would like to listen your some explanation about this.
Okay, sure. First of all, let me put it like that. Silver and copper are the two that can be grown in single crystalline form. We are seeing aluminum, nickel, iron, gold, all different sorts of nanowires as well, especially using anodic aluminum membranes. So the channels in the membranes allows you to grow nanowires in there, and later on you have to dissolve the anodic membrane. Then they are polycrystalline. So if it is polycrystalline, the conductivity is not as good as it would be on a single crystalline material. Plus, the scattering issues start dominating on their surface, so they are not as transparent as a single crystalline metal either. So, but as I said, silver and copper are the ones can be grown in solution methods, not like templated methods. and they are single crystalline. So these are the advantages. And I think in that regard, the others can or should at some point be engineered, but I think for the picture that I draw today, the stability for the others are going to be even worse. For instance, like aluminum, it's going to be worse. And the cost on the other side, for instance, like gold, is start going to be dominating. So the gold salts are highly expensive. So if you are thinking that making nanowires of 60, 70, 80 nanometers in diameter made up of gold, so the cost is going to be a metric there. But nickel or some other, or more like refractory metals can be tried in that sense, as far as I believe, to be an alternative to silver and copper. I hope I answered your question.
Thank you very much. Especially, I wanna visit you and your team to see lots of things. I know from the Shahin, our chairman of this session, our friends listen lots of good things. Thank you very much again, your presentation and your studies. Thank you, Dr. Shahin.
Thanks for the invitation.
I'd like to thank Professor Nolan again. Now we can move on our next invited speaker, Hugies Guralt from the Bruker AXS GmbH. Herr Guralt will give us a talk on structural characterization of ultra-thin platinum film using grazing incidence X-ray diffraction geometries. Herr Guralt?
Yeah, can you hear me?
Yes, we can.
Okay, thank you. Maybe let's start with a question. Have you ever been in a situation, for example, where you are in the middle of a crowded room and you are trying to be heard by someone which is sitting at the other side of the room? That person might be able to detect you, but the chance that she can really understand what you want to express is quite limited because your voice is just covered by all other people's voice. That exact situation is very similar to the one we face in thin film diffraction, where we want to try to isolate the contribution of a very tiny volume out of the overall sample signal. So similarly, we may be able to detect the presence of a phase, but it's much more difficult to tell more details about the material structure. However, there are techniques to overcome this challenge, and that's what we are going to address today. So hello from my side. My name is Hugues Guéraud from Bruker AXS. Bruker AXS is one of the key suppliers of X-ray analytical techniques, and X-ray diffraction is one of them. Over the last 18 years as a thin film diffraction expert, I've been helping and advising a lot of Bruker customers and how to get, help them how to get the most information out of their thin film material. Today, I would like to address dedicated diffraction method that can be set up to investigate challenging samples that sometimes we call ultra-thin films with a thickness range of about 10 nanometer or even less. This talk will also be an opportunity for me to present the performance of a recently released equipment designed for that purpose. Before I go into my talk, I would like to have a short review on for what people use grazing incidence diffraction. So I went on Google and I make a search. I was typing grazing incidence diffraction and thin film. And I had a lot of examples, and I just picked a couple of them just to see what people do with grazing incidence diffraction. So in this first example here, this is an iron nickel thin film, and the people exposed this thin film, probably during the growth, to different nitrogen atmosphere, from 25% up to 100%. The goal of this GID measurement is to observe changes in the material. So we see that first we start with a phase. This is the 111 phase, 200, and 220 of the initial phase, or at 25% nitrogen. And if you increase the content, you see that at some point, you have a phase transition. So this is the goal of this measurement. And actually, it did a very good job. So we were able to observe what's going on. But I would say this is pretty much qualitative. If I would look this as an with an expert eyes, I would say, well, maybe it's a bit noisy. Maybe the content statistic could have been improved. But for what it was supposed to do, it was perfect. This is another example of even thinner layer. This is a 35 nanometer zinc oxide layer measurement in the so-called coplanar grazing incidence diffraction geometry. We'll come back to that later. We'll have some explanation about the different measurement geometries. But here what we see is that this is the initial material. This is 35 nanometer of zinc oxide, so a very tiny diffraction volume. And by heating, you see clearly some change in the peak intensity. Right? So the peak intensity ratio is changing from reflection to reflection, which is an indication of a change into the preferred orientation of the grain. Again, you could say, well, maybe the step size is too small, maybe it's a bit noisy, but for what it was supposed to do, it did the job. So what's my point here? My point is that most of the thin film XRD analyses are typically performed to extract qualitative information. People run this measurement because they are so challenging. There is so less material that you don't want to measure endless time in order to have a good scan, because you know it will take you hours or days if you don't set up the right measurement approach. So they use it to validate the presence of a phase, but and it means that they actually measure on a pretty small scanning range, 30 to 80 degrees, while probably your diffractometer can cover a much wider range. So my point here, and that's actually the key message of my talk for today, and that's what the takeaway I would like you to get here, is that the grazing incidence diffraction pattern contains actually a lot more information about the structure, about some strain property, about some crystallite size. And for that, you need to have high quality data. So you could think for thin film or even for ultra thin film, this will never work on the lab equipment. That's way too challenging. So I probably need to go to large equipment. This is the next point I want to convince you, is that laboratory equipment are well suited for analyzing the structural properties of those ultra thin films. So what we are going to see during this talk is the investigation of an ultra thin film of 100 angstrom of platinum. This is a standard from PTB, deposited by pulse laser deposition. And we are going to analyze this film with a newly released equipment at Bruker. This is the D8 Discover Plus, which will allow to set up dedicated diffraction geometry for thin and ultra thin films with different scanning direction. We will, of course, be able to identify the phase, but my point here is that we will also be able to get much more information, like an accurate lattice parameter determination, information about the microstructure, and also information about the strain status. So why is thin film diffraction so challenging? You have here a thin layer, and the layer is characterized by basically two parameters: mu, which is the linear absorption coefficient, and T, which is the thickness of the layer. The product of those two will help you to understand how deep X-ray will penetrate into the material. If you have a more dense material, it will penetrate less. If you have a thinner layer, it will go through very easily. So these are parameters to take into account to optimize your measurement condition. If you try to measure this sample with a standard diffractometer, a powder diffractometer you may have in your lab with a theta goniometer, this is a symmetric diffraction, so tube and detector move simultaneously. You will have, as you see here, a very large penetration depth into the material. And probably the substrate signal will dominate the overall diffraction pattern. A much better strategic way to measure this kind of sample is by using the same equipment, try to decouple the position of your drive. So instead of staying symmetric, you incline your tube on one side, we're having a very grazing incident angle, and you keep it fixed during the measurement. And what you do then, you simply scan the detector to screen the Bragg conditions. In that case, you will be able to control the penetration depth into your layer and hopefully emphasize the signal of your layer. So let's see an example. This is an example of a 20 nanometer indium tin oxide thin film on top of glass. If you measure it like you would measure a powder diffractometer, a powder sample, you see that you end up with a tremendous contribution. This is those big, large hump here, tremendous contribution of the amorphous glass substrate. That's those big humps you see. And on top of it, you see some few peaks here that most probably come from the top indium oxide 20 nanometer layer. But the layer signal is in a range of less than 1%. So, well, you could say, I'm happy I have 4 peaks from indium tin oxide, so most probably indium tin oxide is in, but you cannot do much more. You cannot really analyze the structure of the layer. If you now set up an extremely precise GID measurement at a selected incident angle, and this incident angle is determined by optimizing the penetration depth of X-ray with some alignment scan. Look at the scan you can get. This is the exact same sample on the exact same machine. You simply have changed the position, the relative position of tube and detector. So this is the appropriate way to measure thin films. We have emphasized the layer signal, and we have basically almost vanished the substrate signal. And those data have good enough quality, very smooth peak shape, pretty large angular range. So we can think of doing some structural analysis on this sample. The question is also sometimes how to know if I have to set up GID or if I can still do some lock couples or some symmetric scan. Again, the mu-T coefficient helps you here to understand where to go. We have here on this plot, this is the thickness of the layer. We have made the calculation for a platinum layer, which has a pretty high absorption coefficient. And we display here the relative intensity in symmetric diffraction of the platinum layer versus the substrate signal. What we see, we can actually define different ranges. What we see is that above 1 micron, there's no need to set up any GID measurement because you hardly here, you don't penetrate into the substrate, you just start penetrating somewhere here. So the substrate contribution will be very, very small in your diffraction pattern. So here, for, I would say, thick layers, and I would rather call it a coating, you can keep on using your standard theta-theta diffractometer. Here we define an intermediate range, and actually this crossing point strongly depends on your material. If it's somewhere here for platinum, for an organic layer, it may shift much higher here, so you may need to set up the GID much earlier. But a range here for platinum between few tenths of nanometer to 1 micron, you would still be able to nicely identify your layer because you will have a mix of intensity between the two contributions. So this is what I would call the thin film regime. If you now go for even thinner layers from 1 to 10 nanometer, then the layer contribution is almost invisible. You are below 100 or 1,000th compared to the substrate signal. And there's no way out than doing GID measurement. So let's see what we need to set up to perform grazing incidence diffraction. So in grazing incidence diffraction, you need to use extremely low incident angle. Here we have an incident angle of 1/2 degree, which is typically what we will need to use for those very thin layers because we want to avoid the signal below. If you use a 100 micron exit beam out of your source, and due to the footprint effect at low angle, you will have a footprint size of 10 millimeter already. And 10 millimeter is probably the size of a typical research sample, 10 nanometer, maybe 10 millimeter, maybe 20 millimeter. But that means that whatever beam size you have out of your source, you will have to strongly reduce the size to something in the range of 100 micron. So we have here compounding issues that on one side, you have a very low grain statistic that will deliver you a very weak signal intrinsically. So you would like to illuminate it with all the flux you can deliver, but the problem is that you have to confine this beam because of this footprint problem. If you don't confine it, you will over-illuminate your sample and you will simply generate more background. You will not get any additional count from your layer. So what we need to make sure to have a successful GID measurement, you need to use X-ray component that deliver a very high flux density in order to be able to do proper evaluation. Another property from the thin film, the thinner you go with the film thickness, the more anisotropic properties you will have in your material. One of them could be, for example, the anisotropic crystallite size. If you reduce the film to a few nanometers, most probably the in-plane crystallite size might grow broader than the out-of-plane that will anyhow not be thicker than the layer thickness. So the question is, how can I investigate those properties in different directions while keeping my grazing incidence beam? Another parameter you may be able to extract is the lattice strain, and this mostly acts in the plane. So again, I have to measure information out of the plane and in the plane. So that means you will need to have a goniometer accessing specific diffraction geometries, the so-called coplanar and non-coplanar geometries. In order to understand this, I would like to show a couple of minutes video, a kind of tutorial that explains what coplanar and non-coplanar diffraction is. So I invite you to watch quickly that video and we come back in a couple of minutes.
Coplanar and non-coplanar diffraction. An X-ray diffraction experiment consists of a source, a sample, and a detector. The angle between the incident and diffracted beams set the atomic distance and direction being analyzed. This distance and direction define the diffraction vector. Additionally, the angle of incidence is tied to the depth of penetration. In a coupled scan experiment, the distance and penetration will change throughout the scan. However, the direction being measured will not change. This type of measurement can be used if our sample has many randomly oriented small crystals or one carefully oriented large crystal. If the sample is a coating, it is often desired to limit the depth of penetration. This can be accomplished by fixing the angle of incidence at a shallow angle and only moving the detector. As the angle of incidence is fixed at a shallow or grazing angle, this technique is called grazing incidence diffraction, or GID. This limits the depth of penetration to several microns, but the direction of the diffraction vector now varies during the experiment. Due to the changing diffraction vector direction, the sample must consist of randomly oriented crystallites. Both of these experiments, the coupled scan and grazing incidence scan, are referred to as coplanar scans, since the source, detector, and diffraction vector reside in the same plane. If the sample consists of a very thin layer, just nanometers in thickness, or if it is required that the diffraction vector be oriented precisely in the surface plane of the sample, a different technique is required. When an X-ray beam enters a sample, it bends slightly towards the surface due to an effect called refraction. This angle, known as the critical edge, depends on the density of the material. By setting the angle of incidence at the critical edge, The X-ray beam is channeled along the surface, reducing the penetration depth to just a few nanometers, and redirecting the diffraction vector in the plane of the sample surface. While traveling along the surface, the X-rays will encounter atomic planes oriented perpendicular to the sample surface. The diffracted beam will exit the surface of the sample at the same angle that it entered. To capture the diffracted beam, the detector must move in the direction perpendicular to the classic detector motion. In the case of polycrystalline material, no additional alignment is required. If the sample is a single crystal, the sample rotation must be taken into account to ensure the right diffraction condition is met. Since the diffraction vector is not in the same plane as the source and detector, this technique is known as non-coplanar diffraction. Another common name is in-plane grazing incidence diffraction. Whether the sample that is being investigated is a bulk powder or nanometer thick epitaxial film, careful control of the source, sample, and detector are all important in collecting reliable results. Having access to both coplanar and non-coplanar techniques allow unique insights into your samples.
Okay, welcome back. I hope you enjoyed this education video. And by the way, if you want to have more of those education video, go on YouTube, Bruker YouTube channel, and you will find a lot of those tutorials. But what I would like to do is do a quick wrap up of what we've heard here and just extract what we really need to understand further for our talk here. What we've heard is that, first of all, the source and the detector angle set the atomic distance. This is nothing but the Bragg's law. So at a given incident angle, exit angle, this fix the 2 theta, and you will be able to observe a certain d value. But what is even more important is that it doesn't only set the interatomic distance, but it also sets the direction being analyzed. So this would be the diffraction vector. And this means that only the planes in symmetric diffraction, only the planes which are parallel to the surface will be analyzed. And this will not change during the measurement. This is pretty different in GID. In grazing incidence diffraction, the direction of the diffraction vector varies permanently during the measurement. Your incident beam is fixed, your detector is moving. So that means that the higher the 2 theta you go, the more inclined is the grain. So you have a variation of the plane inclination you are investigating, and we will see that this will be a very big advantage for residual stress evaluation into your material. What we've also heard is the so-called refraction effect. If you have a very low incident angle at your surface, you will have a refraction effect at the interface. That means that your incident angle you thought you had set up is actually modified at the interface. And it also means that the diffraction peak position you would have expected is also shifted towards slightly higher angle. So that means that the position you measure in GID is most of the case an apparent peak position. So you also have to take this into account in your peak position evaluation. Finally, what we've learned is that in order to do a complete evaluation of your ultra-thin film, you will need to scan and investigate your sample characteristic towards different direction, towards the surface normal direction, this is the coplanar direction, but also in plane, and this is the known coplanar diffraction geometry. So how are we going to set this up? I would like to show you here the so-called the Atlas goniometer that can actually fulfill all those diffraction geometries. This goniometer is equipped with 3 scanning axes. The first one is on the tube side. The second one is on the detector side. This is the classical coplanar diffraction geometry. But there is a third axis, number 3 here, that allows you also to scan in plane while keeping your incident beam grazing on the sample. This will allow you to analyze in-plane properties. What is remarkable on this goniometer is the scanning range of both axes. Both could be up to 150 degrees. And we will see later that the high angle data can be extremely important to either increase the accuracy of your result, but also can be crucial to observe some sample effect on the diffractogram. You can equip the diffractometer with different type of source. This we will review a little bit in the next slide. But very important is whatever the source and whatever the weight of the source, this goniometer will ensure you an extremely high global angular accuracy over the whole angular range, as small as 7,000th of a degree or 15,000th of a degree for both geometry. And this is extremely important because you need to rely on the peak position in order to ensure the accuracy of your results. So actually the goniometer is the core of your result quality. So let's see how we can boost a bit the intensity. You have different ways. The first one is, of course, to consider a strong source. So a micro source might not be, in this case, the best approach because the micro source has a very low axial divergence. So it has a very good in-plane resolution, but probably a slightly lower flux density than the other flux than the other source. What we want to emphasize here is the intensity. And we'll see later, we don't really need resolution. So I would rather consider either the ceramic tube or the rotating anode in this case. If you go for rotating anode, you get 4 times more intensity. Then you need to condition your beam. You remember, you have to put a very narrow exit slit at the exit of the beam in order to control your footprint. So the very first basic approach is just to have an exit slit that would probably be smaller than 0.1 millimeter to reach this beam size because the beam is divergent. If you want to condition a little bit more the beam, you can use X-ray mirrors. You can use a parallel beam Goebbels mirror that will convert your divergent beam into a parallel beam. So you will increase your flux density by a factor 5. And if you want to have even more flux, you can use a focusing mirror that will convert the divergent beam into a focusing beam at the sample surface. Compared to the parallel beam, that's another factor 3 on top. So you see many ways to tune your configuration in order to achieve the best flux density for ultra-thin film investigation. The last component, and this is also a very important one, if you want to do grazing incidence diffraction, due to the large footprint on the sample, you need to use on the primary side here for coplanar GID a solar slit, and for non-coplanar GID, one on the secondary and one on the primary side. And depending on the acceptance of those solar, you may lose again quite a lot of intensity. If you look here, this is the principle of grazing incidence diffraction. You have a pretty large footprint, so the diffracted beam will be very broad and in all directions. So you need collimator plates like displayed here in order to precisely measure a certain 2 theta position. We have a very large set of different angular acceptance. So this defines your instrumental resolution. But I would say for ultra-thin film, I would rather focus on the one that cuts the least intensity. Less intensity than here. Here we lose about 2 orders of magnitude. Here we lose maybe a factor of maybe 1 order of magnitude. So again, better favor intensity rather than the resolution for thin film diffraction. So let's now measure our sample with an optimized setup and see what kind of data quality we can get. So data collection of 100 angstrom platinum on glass. This is the kind of data quality you can get within an hour, which is, I would say, for grazing incidence diffraction, a reasonable measurement time, using this configuration. We have a standard seal tube here, used at 1.6 kilowatt. We have a focusing mirror that helps us to refocus as much intensity as possible on the sample surface. And we have a pretty large acceptance of the solar because from a nano-sized layer, we don't expect grain size. which are going to be so big. So intrinsically, the peaks are broad. So again, better favor intensity than resolution. What we see in the center here also is a set of alignment drives. The most important one is actually the height alignment, the motorized height alignment. If you have a very grazing incident angle and you want to hit the surface, you have to very precisely adjust the sample height. So a Z drive for this kind of analysis is very important. So what do we see here? We have been able, so by the way, you see that even if it's only 10 nanometer, the glass signal has almost vanished. So I think we have nicely optimized the conditions here. Incident angle is around ½ degree. And what we see is that the peaks we observe nicely match with the FCC peaks of platinum. We have all peaks 111, 200, 220, 311, and 222. So we could say, well, job done. Why do we need to worry about anything else? We have everything. If I look a little bit more in details, I see that those peaks are not fitting exactly to the right position. Might be an effect of the refraction, have we discussed before. But if you simply go a little bit further in your scan and go all the way up to the end of the scanning range accessible on that machine, and here we were actually able to measure up to 160 degrees, which is very good because we were also able to catch the 422 peak of platinum. What we observe is that we have a severe mismatch at high angle. So the situation we had before, while measuring only at 90 degrees, we think everything is nice in a perfect world. If we simply extend the scan, and this is only an additional hour, so instead of 1 hour, I measured 2 hours. But it looks like this additional hour gave me a lot of more information. We'll explain that in a moment. If we do the same with the non-coplanar arm, so the in-plane scan, and also going here all the way up to the highest accessible angle here, which was also here in this case, 160 degrees in plane, we also have in 2 hours a very decent diffractogram. So we have all the peaks, and even including the last peak here. So, and this is close to the collision limit, actually. Slightly different configuration. I have a little bit increased the solar acceptance just to get more flux. If I would have kept smaller solar, I would have had to double or triple the measurement time. But here, I think this is not required. The instrumental resolution can be easily characterized and later on accounted in your microstructure evaluation. So if we just overlap and compare the GID, the coplanar GID and the non-coplanar GID measurement, and also compared to the theoretical position of platinum. If we look in details over the scan, there is basically no peak where we have a good matching of all three. So the coplanar and non-coplanar at a different position, and the theoretical peak position is also at a different position. If we look at high angle, also, there's a lot of mismatch. So here we need to understand, we need to put a little bit more maybe of physics inside to try to understand how come that we have different peak position just by changing the direction of orientation. One of the key reasons for this shift is actually the residual stress in your thin film. If you consider here a stress-free cubic lattice, and you deposit this material on with a very small thickness, it's most probable that the lattice will be strained. It depends on the growth condition, it depends on the method of growth, it depends on the temperature of growth, it depends on many things. But my experience is that the thinner the layer, the more chance you have to find strained lattices. You remember that grazing incidence diffraction will measure grains which have a variable inclination. And definitely those planes measured with this diffraction vector here, that we can also recognize here with a psi angle with respect to the surface normal, those planes will probably have a different strain status than those plane when we reach the end of the grazing incidence scan. So this is the origin of a strong shift if you have a high strain. And this is only possible to observe if you go to higher angle. So what we are measuring is, with X-ray diffraction, is the D-spacing. And if we involve with the elastic theory some elastic constant of the material, we will be able to extract the residual stress into our material. So we will have to see how we can implement this in our final refinement model. As I said just before, the high angle range is crucial to identify and evaluate accurately the residual stress in your material. If you would simply measure from 30 to 90 degrees, the residual stress, the shift due to residual stress is lower, and we could even think almost constant. It's not really constant, but you remember the small peak shift we had on our low scanning range maybe can be attributed to this effect together with the refraction effect. But since it's almost constant effect at low angle, we were not really able to understand it. If you scan at higher angle, you see how tremendously the shift acts on the peak position. Here we took a calculation for a stress layer of 1 gigapascal, so 1000 megapascal compressive stress. That seems to be a big number, but that's not, that can be often the case in very thin layers. So you see here, by measuring at high angle, we have actually identified something we would not have seen by scanning at low angle. If you consider the non-coplanar, the situation is different because the strain is in the plane and isotropically distributed in the plane. So here while we will scan, there will be no angular dependence of the strain. So this will directly act as a strain on the stress-free parameter. So this will be the lattice parameter we are going to use for the in-plane data. So important to go to a high angle to see that, but there's also other advantages. Even if you have no stress. If we consider our Bragg law here, and you make a differentiation to estimate the relative error versus the maximum scanning range you have achieved, you go that if you measure up to 90 degrees, you end up into this kind of accuracy. But if you extend it up to the maximum accessible range, you will actually increase your lattice parameter determination by a factor 5. So I think it's probably worth spending another hour and make sure you can have even more accurate results. This improvement is also observed for other parameters, the microstructure parameters, crystallite size and microstrain. They have those angular dependencies. And you see again, if you measure up to 90 degrees, or if you measure up to the maximum angular range, you will increase the accuracy on those parameters for both parameters by a factor 3. So let's go into the final part now and see how we are going to refine those data. And with all what we've learned, we are probably able to build a consistent model with a real physical meaning. This is the model that has been used to refine the 2 scans in the 2 geometries. So we talk about 2,600 data points, and they will be refined with only 5 refinable parameters. And those parameters, they have a complete physical meaning. What are those parameters? Those parameters are the stress-free lattice parameter, A0, the residual stress into the material, in and out of plane crystallite size, and the microstrain within the crystallites. And you see those parameters intervene on both geometry, different ways. The peak position in coplanar, it's a combined effect of the stress-free, so the lattice spacing of the stress-free material, the effect of residual stress, and the effect of refraction. Those three contributions together contribute to the overall peak position in coplanar diffraction. In non-coplanar diffraction, we will refine the stress in plane, and that will give us directly the peak position. So how does it look like? And first of all, how are we going to refine those data? To refine those data, I have used the well-known Topaz software from Bruker, which is the state-of-the-art software for powder diffraction. It has all the crystallography in we need. The only thing which is not in there as a default in the graphical user interface is the stress theory. But the beauty of Topaz is that you can access a launch mode, an editor mode, where you can actually implement the physics you want into your refinement. So without going into the details, but just to show you how simple this can be, this is the original code for a phase with a name, a space group, and a lattice parameter. And just by adding one line in the code here, this is the delta 2 theta we've seen before. This is my 2 theta offset created by the stress, which is here. So with adding one line in the code, I have put the stress theory into Topaz. So it gives actually to Topaz a kind of unlimited applicability because you can put whatever you want inside. And by doing this, we are able to simultaneously, and in a very short refinement time, fit the two curves simultaneously with a consistent model by only refining 5 parameters that will apply differently on the 2 different geometries. The different plot is extremely good. So we have been able to achieve the right peak position, especially due to the stress. And you see that we have almost minus 700 megapascal, so compressive stress into this material. We have been able to estimate the crystallite size out of plane and in plane. So there is a small aspect ratio here, the microstrain inside. And even more important here, despite of the shift of the peak in all directions due to different effects, the stress-free lattice parameter we obtain is very much in line with the literature numbers we can find here in the Platinum Metal Review here. 39236, 39232. This actually reinforce the model because yeah, there's so many different effects that this is a good point that we are back to the real stress value. Okay, so I think I've reached now the end of my talk, and I hope I convinced you that you can do a good job on thin film and even on very thin film, and that you can do probably much more than just a qualitative evaluation. Try to use the full potential of your machine. Use larger scanning range if you can, because most probably there is more behind the curtain to be discovered. And with that, I would like to thank you for your attention, and I'm open for some questions.
I would like to thank Herr Guralt for his presentation. I have a question actually. I would like to ask. The previous speaker, Professor Nuland, talked about the ALD deposition of nanowire thin films. Maybe let me show a small example. Here, for example, as you can see, nanowires cannot form a continuous film. So as an overcoating here, for example, alumina can be coated over them via atomic layer deposition. And with some post-processing, the crystallinity of those alumina, conformal alumina, very thin films on nanowires can be increased.
Excuse me, I cannot see your screen.
Okay, let me.
sharing his screen. Yes.
Let me. Can you see now, Hergerat?
No.
No.
Is it the Excel file you show?
No.
I see an Excel file. I mean, that's what I had on my. You're not sharing your screen. At least I don't see it in the session.
Okay, sorry. Let me try again. Can you see now?
Yes, yes, yes, yes.
Okay, so here is the point. These are copper nanowires. They can be coated on a surface as a two-dimensional networks, but they don't, as you can see, they don't form a continuous film. In order to increase their stability, it's possible to coat alumina very thin films on those nanowires via atomic layer deposition. As you may know, here is the example. The core is the copper and the shell is alumina. And on those materials, alumina can be coated as a conformally. It's not like a continuous 2D structure, rather than it can be considered as a 3D structure. So with some post-processing, at this actually, generally up to maybe 50 nanometer or something, they're not very crystalline. With some post-processing, it's possible to increase their crystallinity. So had you had a chance to check such, how can I say, rough materials, rough thin films actually, or did you get any feedback from Bruker users on the crystallinity check of those materials?
Well, I think this might not be very much different from what I've shown here. What is the substrate? I mean, are they deposited on a single crystal substrate or?
Silicon substrates are generally preferred, actually.
Yeah.
First, a couple nanowires can be coated as a 2D network structure, and then atomic layer deposition is applied to form a conformal coating. It can be around 20 nanometer or something. Here is the example is 50 nanometer alumina, but there, since those materials don't have high temperature stability, so the atomic layer deposition processing is applied at a very low temperature. With some post-processing, the crystallinity can be increased, but it is really difficult to.
No, I think there is no problem. You can use the same technique. So here, what you want is actually to focus really on the wires. You want to try to avoid the single crystal signal. Of course, the single crystal signal, you should be actually pretty unlucky to catch it if you do a symmetric scan, because you probably maybe have only one reflection. But if you catch it, that will just cover the whole diffraction pattern compared to this very small intensity. So I would advise you go into grazing incidents and you perform your detector scan, and you should observe the crystallinity of the different components here. The only risk is if you have this coating around that would be too thick and really cover your wires too much. Maybe you have a problem of penetration through the surrounding coating, and then you cannot see the material inside. So this is all about X-ray absorption.
Okay. I would like to thank Herr Duralt again.
Sorry, may I interrupt you?
I think there's a question.
Yes, please.
Yes.
Is it possible?
Yes.
Yes.
First of all, I would like to thank you for your very advanced and kind presentation. I am from Istanbul Technical University. May I ask one question, maybe two questions, and I would like to apologize to you because of my question maybe a little bit out of your speech. So, as you know that, as we know that, experiment duration is important to take the results and evaluate them, as we know very well. And in this point, one question is rising in my mind because of we are in the digitalization of the life. So please please give a little bit more recommendation of you about my question. How did we explain the behavior when there are those who move away from conventional behavior of the end of the analyze? I mean that to investigate the surface properties, we use gazing incidence X-ray. When we are doing the diffraction experiments using only gazing angle X-ray, are there any application of the artificial intelligence for angular factor correction in the thin film X-ray diffraction of the your devices? So I mean that our experimental results should be under our configuration sets of the devices. So is there any application of the smart XRD devices? Thank you very much.
Well, I'm afraid I have not completely understood the question.
Sorry. My question can be classified in two categories. One of them is dealing with the combination of the artificial intelligence with the XRD devices. So artificial intelligence application can be acceptable for the smart XRD devices. What is your recommendation in this point? And another question is dealing with the when we examine the behavior during the experimental studies, if there is one result that is away from the conventional behavior, so how can we examine the result? We can repeat again the experiment, or we can use some tools of the devices. Thank you very much.
Yeah, these are difficult questions for me. Regarding the artificial intelligence, there is definitely possibilities to, in the near future, probably to automate a lot of things we are doing here, because X-ray diffraction is a pretty well-known and established technique. We have a lot of database about known material. So there is a lot of things that can be routinely done, like phase identification, or advising for a certain measurement condition. This is probably where artificial intelligence can help in that direction. I would agree with that. I have to apologize again, but I think I again missed the second question.
Okay. I would like to thank Herr Güralt again for this nice presentation. Dear audience, this is the end of the morning session of our conference. Professor Ateş, would you like to add something else?
I would like to thank Mr. Gerald Hodges. Thank you very much for your good and informative presentation and support us. Thank you very much to you and all Brookyer family. Thank you, Dr. Şahin Coşkun.
You're welcome.
Thank all.
It was my pleasure.
You're welcome. I would like to thank all organizing committee. As I said earlier, this is the end of the morning session of our conference. The session will be continue with 1:30. So I would like to say goodbye to everyone for joining us in this great event. Thank you and goodbye.
Bye. Thank you.
Thank you. Goodbye.